Hello, College Algebra. This is section 2.3, and we're going to be looking at functions. What is a function, and the difference between a relation and functions. We're also going to look at domain and range, determining whether relations are functions. Something called function notation, which you've seen before. And then we're going to be looking at increasing, decreasing, and constant functions. Okay, this is the definition of relation. A relation is a set of ordered pairs. And that's it. So any ordered pair that you can think of is a relation. But not just any ordered pair or set of ordered pairs can be a function. So this is what a function requires. A function is a relation in which for each distinct value of the first component, so x, of the ordered pairs, there is exactly one value of the second component. What this means is for one x value, there must be one y value. Like the x value cannot go to multiple y values. Now, two separate x values can go to one y value, but not the other way around. So we'll look at some examples here in just a little bit. So here we have, it says decide whether the relation determines a function. So what I'm going to do is put it out into xy values, like -4, -4, -3, and 3. And here are my y's, 0 and 1. So here we have 4 going to 0, -3 going to 1, and 3 going to 1. This right here is a function because there is each distinct x value has exactly one y value. Okay? Alright, let's do the same thing on this one. Let's separate it out into its x and y values. So we have 2, 3, 4, and 5. 2, 3, 4, and 5. So we have 2 going to 3, 3 going to 2, 4 going to 5, 5 going to 4. Okay, again, because each distinct x value has exactly one y value, this is a function. Okay, let's do it again. I'm going to have an x and a y column and state -4, 0, 2, and then -3, 3, 6, and 8. Okay, so -4 goes to -3 and 3. 0 goes to 6, and 2 goes to 8. So because this x value does not have one distinct y value, because it goes to two y values, it is not a function. And there we go. That's what determines a function or not a function. Okay, another way we can look at relations is through something called mappings. Mappings from one set to another. In the example below, the arrow from 1, let's see, this right here, this arrow from 1 to 2 belongs to the order pair 1, 2. And then we have -2 to 4, so that's 2, 4, and 3, 4. Okay? So this is just another way you can map your functions or your relations. Okay? The mapping for relation H, which is not a function, the first component, -2, is paired with two different second components, 1 and 0. So y'all see that. So whenever your x values are paired up with two separate y values, then this is not a function. It's a relation though. Okay. Note, another way to think of a function relationship is to think of independent variable as the input and the dependent variable as the output. That's how I often think of it anyway. Kind of like a processing computer program or calculator or something like that. Okay. Another thing we're looking at in this section is something called domain and range. I know you all have studied this before in Algebra 2. And if you didn't understand it then, maybe you should really try to understand it now. This section revolves a lot around, or this whole chapter revolves a lot around a domain and range. So if you don't understand it, please ask me more questions about it during class and I will help you as much as possible. So in a relation consisting of ordered pairs, x, y, the set of all values of the independent variable x is the domain, and the set of all values of the dependent variable y is the range. So here in this example it says give the domain and range of the relation and is the relation a function. So let's look at it this way. I'm going to state the domain. Is this set right here? -4, -1, 1, and 3. And then the range is -2, 0, 2, and 5. Well, if I were to look at it this way, each one of these x values goes to one y value. Therefore, it is a function. And we stated the domain and the range. So domain, just state the x values in a set, and the range, state the y values in the set. Put together as a set. And there you have it. Okay, here we have a mapping. It says give the domain and range of the relation. Is the relation a function? So domain and range, pretty simple here. Domain comes from what's in this blue circle here. So 1, 2, and 3. And then the range comes from what's in this red, or I guess pink circle there. 4, 5, 6, and 7. And because the values of 2 go to 5 and 6, this relation is not a function. Okay? Alright, give the domain and range of the relation. Is the relation a function? Well, let's see. So domain We got negative 3, 0, 3, and 5. And then the range is 5. So now each x value goes to one y value. Although they're the same y value, it doesn't matter. This is a function. Okay? It can't go the other way around. Two different y values cannot go to the same x value, but a whole bunch of x values can go to the same y value. So this is a function. The vertical line test, so if you were to have a drawing or a graph of your function, this is a really good test to use to test to see if your graph of your relation is a function. Okay, so what it says is if every vertical line intersects the graph of the relation in no more than one point, then the relation is a function. So let's do this vertical line test. So we're going to give the domain and range of the relation and use the vertical line test to determine if the relation is a function. So domain. Okay, all of your x values, which is negative 2 and 4. And then your range, which is 3 and 0. Whoops. And if we were to use the vertical line test, well, right here, it would test, and we have 2 points going through that vertical line, which is stated that only one can go through a vertical line in a given drawing of a function. So this breaks the rule twice, actually, so this is not a function. Okay? Let's look at another one. It says, give the domain and range of the relation. Use the vertical line test to determine if the relation is a function. So, because the x values go forever on in this direction and this direction, the domain is all real numbers. And remember, all real numbers in interval notation is negative infinity to infinity. Now let's look at the range. Same goes for the range. The x or y values go forever up and forever down. So all real numbers for that one too. So negative infinity to infinity are both the domain and range. And for every x value, there is a different y value. And you can see that with a vertical line test at any point on this graph, it will pass. Okay? So, what we're going to say here, it does pass the vertical line test, therefore, it is a function. Okay. Next, so here we have, it says give the domain and range of the relation, use the vertical line test to determine if the relation is a function. Well, here, let's look at the domain. It begins here and covers the x-axis from negative 5 to 5. So that there is the domain. -5, which needs to be in brackets. -5 to 5. And then the range, let's do it from here, goes from 3 to -3 along the y-axis. So the range covers -3 to 3. There's the domain and range in interval notation. Now, if we were to plot a vertical line on at any point in this relation here, it would cross this relation's graph twice in many cases. So what this tells us, it does not pass the vertical line test, and it is not a function. Okay, there we go. All right, another one, it says give the domain and range of the relation. Use the vertical line test to determine if the relation is a function. Okay, so domain on this one. If we were to look at the domain, we would see that the x values go forever on in the negative x direction and in the positive x direction. So this is all real numbers, or in interval notation, -infinity to +infinity. And then the range of this function. We have, for this type of graph, we have to see where it begins or where it ends. And where it begins, remember, reading a graph, we always go from left to right when we're reading for the domain, and then when we're reading for the range, we read the graph from the bottom to the top. So from the bottom, this graph says it extends forever down into the negative range, and then it goes up to this point right here. Okay, so the range for this function, or for this relation, I haven't determined if it was a function yet, is from -infinity to this point right here, which is -2, 4, and we just need the y value, so we need 4, and it is included. And so for this one, if we were to plot any vertical line, you could see that it will pass this vertical line test, which means it's a function. Now, let's look at this. It says determine if the relation is a function and give the domain and range. Well, we've already looked at a linear graph and determined that it was all real numbers for the domain and all real numbers for the range. So there we go. Kind of already done this one. Sorry for the redundancy here. It doesn't hurt though. All right, range, same thing. And any linear graph is going to be a function. It's a linear function. So function. Okay. This is a quadratic. All quadratics are functions too. And you can see wherever the vertex is of the quadratic is where the range begins or ends. And then for the domain, it's always going to be all real numbers. So domain of this function is from negative infinity to infinity, and then the range. It begins right here at this vertex, which is 2, 3. Oh. It's going to be included, so put a bracket. 3 to infinity, because the rest of it goes upwards, positive values. So there we go. And I've already said all quadratics are functions. Now on this one, if it was the absolute value of x, or y equals the absolute value of x, then this would be a function. But you can see that by the vertical line test, it would not pass it. It crosses it twice, which is more than once, and it is not a function. So not a function. But we can still determine the domain and the range of this relation. The domain, all of the x values. So the x values here begin at the vertex at 0 and go on forever in the positive x direction. So start at 0 and go on to infinity. And then the range is all real numbers, because it goes forever in the positive y direction and the negative y direction. Okay, and we are done with that one. Okay, this one's a little bit different because we have something called an asymptote. See that little dotted line? That is called our asymptote, meaning the point at -2 does not exist, because if we put a -2 in for this function, we would get 0 in our denominator. So when there's a 0 in the denominator, it is undefined. And what this means is our function goes forever over into this up in the positive y direction, and it gets closer and closer to that -2 value, but it never reaches it. Same from this end. It keeps going down, 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 and keeps getting closer and closer to -2, but never reaches it. So that's why you see it never reaches -2. That's why that point is not included. And this is how we're going to state it in our domain. We're going to say our domain it's really all real numbers except for -2, and this is how you state it, from negative infinity to -2. And remember, not included, so put a parentheses around it, and then union it with start back up -2 to positive infinity. See how I did that? I covered this whole range, or this whole domain, and then this whole domain with the other portion of our interval notation. Okay, the range. Again, our range here, let me erase this real quick. Our range does the same thing. We have an asymptote at x equals 0. Sorry, at y equals 0. We have an asymptote. So right here, there's an asymptote, meaning this right here, this keeps going up for a long time but never reaches the x-axis where y equals 0. Same going in this direction. this goes on forever, but never touches the x-axis, y equals 0. So, y equal to 0 is not in our range, but it does go on forever in the negative infinity direction, and then goes to 0, but 0 is not included. And we start back up at 0 and go to infinity. And then that is our range for this function. And I keep calling this a function, even though we haven't necessarily determined that it is a function, but you could see that if we draw a vertical line anywhere on this graph, any vertical line, it would pass the vertical line test. So it is a function too. Okay, function notation. When a function f is defined with a rule or an equation using x and y for the independent and the dependent variables, we say y is a function of x. To emphasize that y depends on x, we use the notation y equals f of x, called function notation. So y'all have seen this before. We can express this right here, y equals 3x minus 5, in the same form right here, f of x equals 3x minus 5. They mean the same thing. And then remember that this symbol right here, f of x, does not mean f times x. What it is indicating that is x is your independent variable inside your function. Okay? So let's do this. It is asking us to find f of negative 3, then what? F of r, and then g of r plus 2. So let's find all three of these. What we're going to do is plug in negative 3 wherever we see x in our f of x function first. And then evaluate that, which equals negative 9 plus 18 plus 4, which equals 13. And then let's do the same for the next one. It tells us to find. It says find f of r. This is just going to be, we're going to replace r wherever you see x. So we get negative r squared minus 6r plus 4. And we are done. Now, referring to our other function, the g of x, we're asked to find g of r plus 2. So wherever you see x, we're going to replace it with r plus 2. And then we're going to simplify that. So distribute the 3 to the r and the 2. And then simplify. And that is it. Okay. So some more things about functions is they can be increasing, decreasing, or constant functions. So what we have here, some rules. It says suppose that a function f is defined over an interval I, and x1 and x2 are in the interval. And So f is increasing on I if whenever x1 is less than x2 and f of x1 is less than f of x2. So what it's saying is, I'm just going to paraphrase these, f of x is increasing if all of your x values are increasing, then all of your y values are increasing. If those two statements are true, then it's increasing. If your x values are increasing, yet your y values are decreasing, getting smaller, then your function is decreasing. Now, if your x values are increasing or decreasing, doesn't matter which, and your y values are staying the same, then it's known as a constant interval. Okay? Okay, this example is asking us to determine the intervals over which the function is increasing, decreasing, or constant. And how we do this is we read the graph from left to right. We never read the graph from right to left when determining increasing and decreasing, okay? So, determining it going this direction, we can see that this portion of the graph is falling. All right? So, it is decreasing from negative infinity. We state the domain in which it's increasing, decreasing, or constant, to, and then to the point of -2. And is not included in this interval because of this little open circle thing we have here. So we put a parentheses. And then the next portion of the graph is constant because the y values do not change. So from -2, which the 2 is included because of the closed circle, and then the open circle on the other side of the constant part means we put a parentheses. Now, this portion of the graph, as it goes this direction, is going up. So that is increasing. And it gets a bracket starting at 2 and going on to infinity. Let me close it out, and that is done. We've determined the intervals for which it's increasing, decreasing, and constant. Okay, so my last example here, we're interpreting a graph, and let's just start with the first question here. It says, over what period of time is the water level changing most rapidly? Okay, whenever you have water level changing, when you have the word changing, this means slope. This is what you're looking for. And so the steeper the slope, the greater the change. All right? So the steepest slope in this graph is this portion right here. I think you would agree with me if we were together in class. This slope right here, there is no slope here, but this isn't changing as fast as this one right here. So what we're going to say is the hours in which it is changing the fastest. So from 0 to 25 is going to be our answer. Let me write that down from 0 to 25 hours. Okay, and then it says, next question, after how many hours does the water level start to decrease? Well, that's this portion of the graph here, because when you go left to right, it is going down. So from 50 to 75 hours. And then how many gallons of water are in the pool after 75 hours? So figure out that. It is 2,000 gallons. And we are done. Okay, so that is all I have for you on interpreting graphs and increasing, decreasing, and constant, and whether or not a function is a function or a relation. And I will see you the next class day. Goodbye, everybody.